Hello everyone. Today we are going to discuss the problem flight routes check from CSES graph problem set. So let's first of all go through the problem. Okay, there are n cities and m flight connections. Your task is to check if you can travel from any city to any other city using the available flights. Okay, so the first input line has two integers n and m, the number of cities and flights. The cities are numbered 1 to n. After this, there are m lines describing the flights. So each line has two integers a and b. This says that there is a flight from city A to city B and all flights are one-way flights. So you need to print yes if all routes are possible and no otherwise. And in the case of no, that is in the latter case, you also need to print two cities A and B such that you cannot travel from city A to city B. And if there are several possible solutions, you can print any of them. Okay. So let's first of all try to understand what the problem is, and then we will see how we can actually solve this. So this is the input given to you. Let's try to go through the input example. So this is the input given to you. So as you can look in the problem, we have four cities, 1, 2, 3, and 4, and the flight routes are marked like this. Like you have a flight route from 1 to 2, 2 to 3, 3 to 1, and 1 to 4. So if you just look in this problem, if I want to go from, let's suppose, city 1 to city 3, can I go? Can I go from city 1 to city 3? The answer is yes. I can go travel like this from 1 to 2 and then from 2 to 3. This means I can go from city 1 to city 3. But if I ask you the same problem, can you go from city 4 to city 2? Can you go from city 4 to city 2? Or can you go from city 4 to city 1? Or can you go from city 4 to city 3? Can you? The answer is no, right? I can't go from city 4 to 3, 4 to 1, or 4 to 2. So the answer to this particular problem will be no. There exist two cities that can't be visited with the existing flight routes, and I can print any of the city, like any of the combination. I can either print 4, 2. This is also a valid answer. I can print 4, 1. This is also a valid answer. Or I can print 4, 3 as well. Like I can't go from city 4 to 2, 4 to 1, or 4 to 3. So I hope the problem is clear to each and every one of you. What do we actually need to print, or what actually the problem wants to say? Okay. Now how we can actually solve this? So to solve this problem, first of all, I would like to make you guys understand the concept of strongly connected components. So this is a very famous concept in case of directed graphs. We also say it as SCC. So let's first of all discuss this thing, and then we will see how we can actually solve this problem. This problem is actually the direct implementation of strongly connected components. So the motive of giving this problem is to make you guys understand this strongly connected components, or how we can actually find strongly connected components in the graph. Okay. So first of all, tell me, what is the meaning of strongly connected components? I hope all of you understand what do we mean by connected components, right? Like let's suppose if I have node 1, node 2, and node 3. Then we have node 4 and node 5. Let's suppose this is. And we have another component like this. So what we say? We say that this is one connected component. What do we mean by connected? Connected means if I travel from any node, if I just choose my starting point as any node, I can go to any other node within that component. I can go to any other node within that component, right? Like this is one connected component. If I start from any node, I can visit any other node using the edges given. Similarly, this is the another connected component. This two in total does not form a connected component, right? There are two connected components in this graph. This is one of the connected components and this is the other connected components. Now, what do we mean by strongly connected components? So strongly connected components come in case of directed graphs. So if I say you like this, that let's suppose you have a node 1, node 2, node 3, and node 4. Sorry, node 4 like this. Okay. If I say you that this is a graph that I have, can I say that this is a connected component? Can I say this? Can I say this? The answer is no, right? Why? Because when I am saying that, like, this might seem as connected, but this is not connected, because the real meaning of connected, what do we mean? That if we start from any node, we should be able to visit any other node in the graph, right? So just say me one thing. If I start from 2, will I be able to visit 1? If I start from 2, will I be able to visit 1? No, right? So this graph, what we say, it is not strongly connected. This is what the meaning of strongly connected is. Strongly connected words come in case of directed graph. That is the first thing you have to understand. Next, what does strongly connected mean? Strongly connected means that if we start from any node as our starting point, we should be able to visit any other node in that strongly connected component. Basically, what we say as connected in case of undirected graph, we say strongly connected in case of directed graph. Okay. Like for example, if I give you this particular graph, let's suppose this thing, 1, 2, 3, and again an edge this. So you can clearly see that this is a strongly connected component, because if you start from any node as the starting point, you will be able to visit all other nodes in this particular component. So I hope this thing is clear to you guys, that what do we mean by strongly connected components. Now, to understand or to find strongly connected components in the graph, there are two famous algorithms basically, out of which we are going to today discuss the algorithm, Kosaraju's algorithm. So today we are going to discuss this particular algorithm to find strongly connected components in the graph, and it is going to be very interesting. Let's go through it. So for this algorithm, this is the input that I am going to take, and as you can see in this graph, we have some connected components. Let us just identify them first. So if you see, this is one connected component that I have, because in this component, if you start from any node, you will be able to visit any other node. Just see. If you start from 1, you will be able to visit 2, 3, and 4. If you start from 4, you will be able to visit 1, 2, and 3. So this is one connected component, right? Okay. So this is one strongly connected component, as you can see. Okay. Next. This is another strongly connected component, right? This is another strongly connected component that you have. Next. This is another strongly connected component. This is another strongly connected component. You might be guessing that why I'm not saying this as a strongly connected component, this whole. Because if I start from any node, 1, 2, 3, or 4, I will be able to visit 5. So you might be guessing why I am not saying 1, 2, 5, 3, 4 as a strongly connected component. Why this is not a strongly connected component? Yes, you guessed it right. Because if I start from 5, I won't be able to visit any of the node 1, 2, 3, and 4. When I am saying that a component is strongly connected, this means if I start any node as my starting point, I should be able to visit all other nodes in that component, right? So you can see this is one connected component that we have. This is the another connected component that we have. And this is the another connected component that we have. Strongly connected basically. So in this particular example, there are 3 strongly connected components that we are able to figure it out. And I'm going to tell you one more interesting thing. If you just treat one strongly connected component as a single node, like let's suppose we had 3 connected components, right? Let's suppose this is the strongly connected component 1. This is the strongly connected component 2. And this is the strongly connected component 3. If I treat all these strongly connected components as a single node and draw the edges between them, as you can clearly see, from this strongly connected component, we had this particular edge. From this strongly connected component, we had this particular edge to this particular SCC, that is strongly connected component, right? So let me just draw an edge between them. So this is the edge. And you can clearly see as well that from this particular strongly connected component, we have an edge to this particular strongly connected component, right? So let me draw an edge between them as well. Okay. So if I treat every strongly connected component as a single node and then draw the graph, then the graph formed will actually be an acyclic directed graph. And this graph is also known as condensed graph, where you are treating the entire strongly connected component as a single node and drawing the edges between them. It is very much intuitive, like why it will be a cyclic directed graph. Let's suppose it was cyclic. Let's suppose you also had an edge like this, like you also had this particular edge. In that case, this entire component would have formed one SCC, right? This entire component would have formed an SCC. So it makes sense that if we are forming the condensed graph, then condensed graph will actually be an acyclic directed graph. Cool. So I hope this thing is clear to you guys, like why we are able to state that it will be an acyclic directed graph, why the condensed graph will be an acyclic directed graph. Okay. Okay. So now how do we find this strongly connected components? Like at the end of the algorithm, let me just tell you what you will be able to say, like what you will be able to get. At the end of the algorithm, you will be able to get vector of vector, and you will be able to get this thing, and the every object of this particular vector will be the strongly connected components. Like you will have, let's suppose this is the vector that you have. So you will have 1, 2, 3, and 4. Then you will have 5 and 6. And then you will have 7, 8, and 9. So at the end of the algorithm, this is something that you will get. You will be able to segregate every strongly connected component. And an interesting fact, you will also get one of the nodes from this strongly connected component, that you will also get that, okay, let's suppose I take 1. So you will, every strongly connected component, you can just choose one representative node. So let's suppose the first SCC have the representative node as 1. So you will be able to get 1. Then you will be able to get that, okay, from 1 you have an edge to 5. From 5 you have an edge to 7, like this. Like you will also be able to get the condensed graph as well. So isn't it interesting, right? You have the graph, you will be able to form condensed graph from that, and for every component, like let's suppose this is, let's name it as component, not nodes. It won't seem intuitive. So let's name it as component. Let's suppose component 1, component 2, component 3. So you will be able to get the condensed graph as well, and you will also be able to get that in a component what all nodes are present, right? And believe me, this is super important and super helpful as well. Like getting component is one thing, getting the condensed graph for the component is the other thing, and both you will be able to achieve via this particular algorithm. And in the coming problems, when you solve more problems in the list of the CSES graph, you will see, you will just understand why it is super helpful. Okay, for this particular problem we will only need this thing, but in the coming problems you will also need this condensed graph as well. So I'm just going to discuss the entire algorithm and intuition as well, like why it will work. Okay, cool. So let's try to discuss, or let's try to understand what the algorithm is. So just repeating, I am going to discuss the intuition of each and everything that I talk. So just don't rush, or just don't think that I am just saying you the algorithm and I am not discussing the intuition. At the end of the video, you will be able to understand each and every statement that I make with intuition, like why we did it and how we did it. Okay. So let me first say you what the algorithm is. Name we already discussed. We are going to discuss the Kosaraju's algorithm. So the first step for the algorithm says that So the first step says that arrange nodes in decreasing order of their T out time. So this is the first thing, that is the first step that the algorithm says, that you have to arrange the node in the decreasing order of their T out time. Now many of you would be wondering that what is this T out time, right? Okay, so when we perform DFS, like you will be able to understand this T out once we discuss the algorithm. So we'll see this, okay? Don't get confused at what do we mean by T out time. We will discuss this, okay? Now what is step 2? Step 2 says reverse the edges of the graph. So this is very simple, right? Step 2 is very simple. You simply need to reverse the edges of the graph. And what does step 3 says? Perform DFS in this particular order. Let's suppose this is order 1. Perform DFS in order 1 with reversed edges. So whatever we will do, like step 1, step 2, step 3, we are not doing anything different. Like we have already performed DFS. We know how to reverse the edges of the graph, right? Like we can simply reverse the edges of the graph. We can perform DFS in the reversed edges. So we will not be doing anything fancy, but why we are doing a particular step and we need to do that particular step to get strongly connected components is something that we need to know, right? Okay, so how we can actually so let's perform step 1 first, and then we will see like what does T out means. Okay, so just give me a minute. Cool. Can I copy this? Let me take it down. Okay. And let me erase these things. Not Nintendo now. Okay. So first let me get the order of T out in decreasing order. So if you guys remember, if you have watched all the solutions till now before this particular problem, we have discussed a method of topo shot by a simple DFS, right? So if you just perform topo shot in this particular graph, via the DFS method that we discussed, you will simply get the order that we want, that is decreasing order of T out time. Now let me first discuss over here what is the meaning of T out time. T out time means that let's suppose you start a DFS. From 1, and let's suppose the current time is 1, right? The time starts from 1. So from 1 you will visit 2, then you will visit 5, then you will visit every other this component, you will visit 6, you will visit 3, you will visit 4, you will visit every other node, and after that the DFS from 1 will get complete, right? So every time when you visit a node, what we do is we increment the time. Okay. So at the time when the DFS from 1 is completed, that time is said as T out time. Okay. You guys will be able to understand. So let's first of all perform this DFS. So I am going to discuss this T out time only, but the code will be exactly similar to finding the topo sort using the simple DFS algorithm, using the simple DFS that we have already discussed, right? It's very easy as well. You guys will be able to understand over here as well. So you start from 1, okay? From 1, so you marked 1 as visited. Let me mark this 1 as visited. Then you come to 2. So you mark 2 as visited. From 2, you can go to any node. Let's suppose I choose to go to 3. So 3 is visited. From 3, I choose to go to 4. 4 is visited. Now from 4, what are the options you have? The option that you have is you can go to 1. But 1 is already visited, right? So from 4, you don't have any other options for the DFS. So what you do is, in the vector at the end, you write 4. Okay. So in the vector at the end, you write 4. Let's suppose you are maintaining some vector, and in the vector at the end, you write 4. Now you return. So from 1, you went to 2. From 2, you went to 3. From 3, you went to 4. From 4, 1 was the option, but 1 is already visited. So you won't go to 1 again, and you will simply return. Now, since you are returning, this means that DFS from 4 is already completed. So if you try to make things easy, you can just see over here that DFS for like T out time for 4 will be the minimum. What does T out time means? T out time means the time at which the DFS from a particular node is getting completed. So 4 is the first node for which the DFS is entirely completed, right? So T out time for 4 will be least, and hence it is coming at the end. Okay, cool. So now from 4, what you will do, you will go, you will just return back, backtrack, you will come to 3. From 3 again, you had only one option, that is 4, and you have already explored that option. So DFS from 3 is also completed, and you will write 3 over here. Okay, now you backtrack to 2 again. From 2, you have already explored the option of 3. So now you will try to explore the option of 5. So you go to 5. From 5 again, you have two options. Let's suppose I go to 6 first, and you can clearly see that 6, for 6 you have, so you will first of all mark 5 as visited. Then you go to 6. From 6, you have only one option, that is return to 5, but 5 is already visited. This means that DFS for 6 is already completed, and hence you will mark 6 as visited. You will mark 6 as visited, and in your DFS vector, like, you will push 6. Okay, cool. So you will then backtrack from 6 to 5. From 5, you will explore the other option, that is 7. So you will mark 7 as visited. From 7, you will go explore other option 8. So you will mark 8 as visited. From 8, you will explore the other option, that is 9. You will mark 9 as visited. From 9, you will try to explore the DFS option from 9. So you will try to go to 7, but you will see that 7 is already visited. So for 9, the DFS is actually completed. So you will simply push 9 in your vector at the front. Okay. And then you will backtrack. So from 9, you backtrack to 8. From 8, you don't have any other option. So again, you will push 8 in your vector. From 8, again, you will backtrack. You will come to 7. From 7, no other options. So DFS from 7 is also completed. So you will mark 7 over here. Then from 7, you will backtrack. And from 7, if you backtrack, you will go to 5. From 5, you have already explored the both possible option. So again, for 5, the DFS is completed. So you will push 5 in your vector. Again, from 5, you will backtrack. You come to 2. From 2, all options are explored. 3 is explored, 5 is explored. So again, DFS from 2 is completed. So you will simply write 2 over here. And from 2, you backtrack. You come to 1. From 1, all the options are explored. 2 is explored. 3 you can't explore because it is already visited. So again, the DFS from 1 is completed, and you will push 1 in your vector. So now, if you simply see this particular vector, this particular vector have nodes arranged in the order of, in the decreasing order of T out time. This vector have the nodes arranged in the decreasing order of the T out time. Definitely you can't say it as like a complete topo sort, because there is a cycle present in this graph, like 1 to 2, 2 to 3, 3 to 4, 4 to 1. But if you just look from the condensed graph, so you will just notice that condensed graph is arranged in the topological sorted order. Like, you have one SCC component that contains nodes 1, 2, 3, and 4. You have another SCC component that have node 5 and 6. You have another SCC component that have nodes 7, 8 and 9, right? And this was the condensed graph that you got. So you will simply look that one node from this 1, 2, 3, 4 comes before any other node of 5, 6, and this comes before of any other node of 7, 8 and 9. So you can clearly see that over here you have one of the nodes, one and both actually two nodes, 1 and 2 coming before 5 or 6, and one node 5 coming before any other node 7, 8 and 9. So condensed graph will be arranged in the topological sorted order. Okay, we will discuss that why are we actually doing this, why we are actually forming the vector in the order of decreasing order of t out time. We will discuss that. Okay, cool. So I hope this thing is clear how we are actually doing this. This is like the exact code, like the code for this will be exactly similar to how we actually find the topo sort. We are actually finding the topo sort only. So this will be exactly similar. Okay, cool. Now what was the second step? The second step was to reverse the graph, reverse the edges of the graph, right? So let me just draw the diagram for this. Just give me 2 minutes for this. I will quickly draw the diagram for that. So you have node 1, you have node 1, 2, 3, 4, 4, 5, 6, 7, 8, 9. So if I just reverse the edges, let me first draw this thing, this had two edges, 1, 1, 1, 1. Okay, and this had edges as well. So I'm just reversing the edges. Yeah. So this was your node 1, node 2, node 3, node 4, node 5, sorry, node 2, node 3, node 4, node 5, 6, 7, 8 and 9. Okay, so this is the graph that contains the reverse edges. Okay, this is the graph that contains the reverse edges. So we have the order with us. The order is 1, 2, 5, 7, 8, 9. Let me write the order as well over here. 1, 2, 5, 7, 8, 9, 6, 3, 4. So this is the order. Now what we are told? We are told to visit the nodes in this particular order in the reversed graph. Okay, let's try to do that. We will discuss that why we are doing this, why we have got this order. We'll discuss everything, but let's first try to understand that whether algorithm is working good or not, right? Let's first of all try to verify that. So let's try to do this. We will explore in the order of this vector that we got. So let's, so the first node is 1. So let's first try to explore the DFS from 1 in this reversed edges graph. So from 1 if you start, so this 1 will be marked as visited. So from 1 you go to 4. So this I'm just writing over here that 1 is marked as visited. I'm just circling it. Okay. And let's suppose you have a vector. So you have 1 over here pushed. Then from 1 you can go to 4. So 4 is marked as visited. From 4 you will go to 3. So 3 is marked as visited. From 3 you will go to 2. 2 is marked as visited. From 2 you can go to 1, but 1 is already visited and you don't have any other option. So this DFS is particularly, so you will mark 2 as visited basically, definitely. And so this particular DFS is complete. So you have got one strongly connected component. If you just look, 1, 4, 3, 2 forms one strongly connected component, right? Great. Let's try to do the next step. Let's continue our DFS. So first of all, we started our DFS from 1, then we will see from 2, but 2 is already visited. So we will move forward. We will start our DFS from 5. So from 5, if you try to do the DFS, so from 5, you will see 2 is already visited, so you can't go. So first of all, you will mark 5 as visited. You have this 5. Now from 5 you can go to 6. So you will have 6 with you. You will mark 6 as visited. And from 6, 5 is already visited. Again from 5, you don't have any other option. So this forms another strongly connected component. Right? Let's continue our DFS. So 5, we have done till 5. So we will go to 7. 7 is not visited. So we will start our DFS from 7. From 7, 7 is visited. From 7, you can go to 9. So 9 will be marked as visited. From 9, you can go to 8. 8 you can mark as visited. From 8, you can go to 7. But 7 is already visited. So you won't go. You will simply backtrack. And this is the nodes that you get. Now from 8, if you try to do DFS, already visited, 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 visited. So if you just look, you have these strongly connected components with you. And if you just remember, from where did we started our DFS? We started our DFS first of all from 1. Okay. Then we started our DFS from 5. And then we started our DFS from 7. Right? We started our DFS from 1, we started our DFS from 5, and we started our DFS from 7. This means these are the representatives of your all components, like any one node from this component, any one node from this component, any one node of this component. So you will get the condensed graph as well. So this is how you can actually get the things. Like, what are the steps that we followed? We first of all arranged it in the decreasing order of the T out time. Then we reversed the edges, and then we performed our DFS in that T out time order in the reversed edged graph, and we got our strongly connected components. Now, let's discuss that why it actually works. Okay. So let me just tell you one thing. You have SCC1, right? Strongly connected component 1. From there was an edge from SCC1 to SCC2. And from SCC2, you had an edge from SCC2 to SCC3. Right? Okay. Just tell me one thing. If I reverse the edges, how will this graph looks? You have SCC1, SCC2, SCC3. If I reverse the edges, how will this graph look? This graph will look something like this, if I'm not wrong, right? And just tell me one thing. If you reverse the edges of the graph and do a DFS from any one node from SCC2, SCC2 had nodes 5 and 6, right? So if you start your DFS, SCC1 had nodes 1, 2, 3 and 4. And SCC3 had nodes 7, 8 and 9. If you start your DFS from any one node 5 or 6, so you will be able to visit 5 and 6 in the reversed edge graph as well. Just first of all understand this thing. Like SCC, in SCC, even if we reverse the edges, we will be able to visit all the components. Like, right, let's suppose you have node 1, node 2, node 3 and node 4. This is the SCC that you have. Okay. So even if you reverse the edges, like this, even if you reverse the edges, if you start from any node, you will be able to visit every other node from this SCC, right? But what we wanted to make sure that if we are starting from any node, if we are starting our DFS from any node in the SCC, we should be able to visit only the nodes of that particular SCC and not any other node, right? Just tell me one thing. If I would have started our DFS from SCC2, if I would have started my DFS from SCC2, let's suppose node 5, in that case, in the reversed edge, I would have also end up visiting 2 as well. And from 2, I would have end up visiting 1, 4, 3 as well. But is 1, 2, 3 and 4 forms an SCC with 5? Does it form an SCC with 5? No, right? These are two different strongly connected component. So it was very, very essential for me that first of all, I did a DFS from any one node of this particular SCC, and after that, I am doing a DFS from a node of this particular SCC. It was very essential because from 5 in the reversed edge graph, there will be an edge to 2. So if 2 is not visited before visiting 5, in that case, I will end up going to 2 from 5 and that will destroy all my game. So this is very essential. The order is very essential. So I hope this thing is clear to you guys that, okay, if we are reversing the graph, if we are reversing the edges, we will be able to visit all the nodes in the strongly connected component that particular node belongs to. But we just don't want to visit any other node other than the strongly connected component nodes. So to make that sure, it's very important that we visit the node in some specific order. This thing is very clear, right? Now, why we made this particular order? Like why in decreasing order of T out time? Why in decreasing order of T out time? And this thing is very much clear that, okay, this thing is very much clear that for SCC1, if we have a node from SCC1, if I have an edge to SCC2, then what I am pretty much sure is that T out time, maximum T out time for this SCC1 will be greater than maximum T out time for SCC2. What do I mean by maximum T out time? For SCC1, there are 4 nodes, right? 1, 2, 3, and 4. For SCC2, there are 2 nodes, 5 and 6. By maximum T out time for a particular component means maximum of T1, T2, T3, T4. This will always be greater than maximum of T5, T6. This is what I mean. So if this is the case, and now if I will discuss that why this will always be true, but just imagine if this is the case and if I arrange the nodes in the order of decreasing T out time, I will always end up first of all visiting all the nodes of this SCC1 and then I will try to visit the node of SCC2 in the reversed edges graph, right? Now let me just explain why this is always true. Why if I have an edge from SCC1 to SCC2, why I am pretty much sure that maximum T out time for SCC1 will always be greater than the maximum T out time of SCC2. Let me discuss this thing. So why I'm pretty much sure of this? Okay, let's suppose there are 2 cases, right? In SCC1 and SCC2, there are 2 components, right? Okay, let's suppose I first of all enter SCC1. That is, T in of SCC1 is T in of SCC1 is lesser than T in of SCC2. There are only 2 possible cases, right? That either that first of all either I enter SCC1 or I enter SCC2. Okay, if first of all I am entering SCC1, now since there is an edge from one node in SCC1 to the other node in SCC2, can you guys tell me, when I complete the DFS of SCC1, I am pretty much sure I would have already completed the DFS of all the nodes in SCC2. For example, you had this particular graph, right? So over here, I started with 1. This means that the entry time for SCC1 was lesser than the entry time of SCC2 that contains nodes 5 and 6. So when I am pretty much sure that I have completed the DFS of every node 1, 2, 3 and 4 that are part of SCC1, I am pretty much sure that I have already completed the DFS of every node of SCC2 that is 5 and 6. Because there is an edge from one node in SCC1 to the other node in SCC2, right? So from 2, I will definitely cover this particular edge as well. Then only I will say that I have completed the DFS for 2. So I am pretty much sure if the T in time if the t in time of this SCC1 is lesser than the t in time of SCC2, then I'm pretty much sure that max t out time, then I'm pretty much sure that max t out time for SCC1 will be greater than max t out time for SCC2, right? This is clear. What is the other condition? The other condition is t in time of SCC1 is greater than the t in time of SCC2. That is, first of all, I started my DFS from 5. After that, I am starting my DFS from any other node 1, 2, 3, and 4. If this is the case, I know that from this SCC2, I don't have any edge to this SCC1. So if I have already started my DFS from 5, so first of all, I will complete the DFS for that component. So if I do that, I will never end up visiting any nodes 1, 2, 3, or 4. So definitely once I complete the DFS of this component, then only I will move to the DFS of this particular component, right? So in this case, it's very simple that the T out time, again the max T out time of SCC1 will be greater than max T out time of SCC2. In this case, you can clearly see that T in time of SCC1 is only greater than T max T out time of SCC2, because first of all you will complete the DFS for SCC2, then you will start your DFS for SCC1, right? So in this case, T in time is only greater, so T out time will definitely be greater. And in this case as well, T out time will be greater. So I'm pretty much sure that if I arrange the nodes in the decreasing order of the T out time, and then if I perform the DFS with the in the reversed edge graph in that particular order, I will be able to get strongly connected component. So this is again like maybe that it will take you some time to digest. If you just try to think by your own, it's very easy. It's not like too many fancy things that we have done. The only thing was that when we reverse the edges and traverse the nodes, we are always able to visit the strongly connected component nodes. The only thing that we don't want is we visit any other node other than the nodes of that particular strongly connected component. So for that, what we decided that we will traverse or we will do our DFS in the reversed edge graph in a particular order. And what is that order? That order is actually decreasing order of T out time. And why we are doing that? That I made it clear over here. Okay, cool. So now let's come to the problem. Definitely that the problem that we had, that the question asked was that if you start from any node, if you start from any city, will you be able to visit every other city in the graph via the flights given, right? So the question basically wants you to say that is the graph given is an entirely one connected component, strongly connected component. If it is not a strongly connected component, as you can see, we have this strongly connected component and then we have a 4. So basically you have like this. Basically you have like this over here. You have a strongly connected component that contains node 1, 2, and 3. And from there you have as an edge to strongly connected components that contain node 4, right? Actually 2 edges, but let's define by less. Like you have something like this. So definitely if you start from 4, you won't be able to visit any node of this particular strongly connected component 1, 2, and 3. So this graph as a whole is not a strongly connected component, and hence the answer will be no. And for printing the 2 cities you won't be able to visit, just print any city from this strongly connected component and any city from this strongly connected component, and you will be good to go. Okay, let's try to see the code. You will understand it better. So I have taken inputs of n and m, that is the number of nodes and edges, and then we have the graph and the transpose. Transpose basically we have reversed the edges of the graph. Okay, taking 2 nodes, converting to 0-based indexing, you have an edge from u to v, so graph of u dot pushback v, and then in the reversed edges you will have an edge from v to u, so transpose of v dot pushback u. Then first of all we get that decreasing order T out time order. So for that we simply do a topological sort. So we have a visited topo vector and a topo order and insert count as 0. This is actually the same way that we do a topo sort. So I just traverse over the node, and if the node is not visited, I call this DFS topo. So in that, what I do, I first of all mark the node as visited, traverse over all the adjacent node, and then I push this node. Where do I push this node? At the index n minus inserted count minus 1. Let's suppose I have already inserted one node. So this particular node will be the second last node, right? So this inserted count basically tells me how many nodes I have already inserted. So in that I push and I simply insert count. I simply increment this insert count. So this insert count is passed by reference if you just look. Okay. This helps me to tell that at which particular index I am actually pushing back the node. Cool. So once you're done with this, so you have the decreasing order of T out time already arranged. So now you find the strongly connected components. So for that you have a visited vector, you have a vector of vector int components, and I have also kept a representative node. This representative node will contain one node from every component. Okay. Now, first of all, I get the node from topo order of I. I just traverse in order. And if that node is already visited, I simply continue. And if it is not, I do a DFS from that node. So for that, I have a component vector and I do a DFS. So in that DFS, what I am doing, I am marking the node as visited. In my component, I am pushing back that node and traversing over all the neighbor nodes. And if the neighbor node is not visited, doing a DFS from there. Simply a DFS that we do. Once you're done with this, so in my components vector, I push back this particular one strongly connected component. So this component that I will get will be one strongly connected component. So I simply push back that. And in my representative nodes, I push back this particular node. Okay. So in my representative nodes, I have just pushed one particular node from this particular component. Okay. So now at the end, you have all the components. So if the component size is 1, this means the entire graph forms one strongly connected component. So in that case, you are simply printing yes. Otherwise, you print no. And you just print, like, you know that there is an edge from component 0 to component 1, right? There is an edge from component 0 to component 1. So what you do is you simply print one node from component 1 and one node from component 0. That is one node from the second component and one node from the first component. I am pretty much sure that I won't be able to visit the nodes from component 2 to component 1. So representative nodes of 1 plus 1, basically for converting to 1 base indexing, representative nodes of 0 plus 1. And I will be good to go. So this is how you actually get the strongly connected components. And if you look, it is also arranged in the basis of topological sorted order, right? Like if one of the representative nodes will always be arranged, like if you just take one of the representative node from one strongly connected component, and let's suppose I take the one with the maximum T out time, and if I just arrange them, they will be arranged in the basis of topological sorted order with this topo order vector, right? This will be very useful when you solve the other problems as well. But this is how you actually get the strongly connected components in a graph. I hope the video was helpful. Thank you.